To continue the discussion of the Note Graphing Synth as a vehicle for instructing how to create an EaganMatrix overlay, let's take a little look at the application side of the overlay. The code that runs on the Electra One controller that interfaces to the EaganMatrix preset you've just created. Now you're going to need some kind of a programming interface to do this, whether it's from the Electra One or an iPad, whatever it is, you're going to have two things. Number one is a Midi interface that allows you to communicate to the EaganMatrix preset, and number two is some kind of GUI builder or GUI interface that gives the user an interface to control your EaganMatrix preset in a way that makes sense, with nice buttons, dials, whatever it is that you want to create to give the user a nice experience in using your overlay. So let's talk about first the primary things that you're going to need to have on hand for programming. Now, without question, the two most primitive operations that you're going to need to support in your interface are, number one, the ability to write a 7-bit CC to your EaganMatrix preset to do some control, and also the ability to write a polyphonic aftertouch message. Now, these are used in a custom manner by the EaganMatrix. Normally, the polyphonic aftertouch message will have a note on value, and then it will have some kind of pressure value. But the EaganMatrix just uses a data 1 and a data 2, two data values that you'll supply to this aftertouch message to do various things. And all of the constructs that you'll use to interface to the EaganMatrix overlay running on the Osmos or Continuum, that preset will be interfaced to using a combination of these two messages. Now, I'm talking about the Electra One that has a Lua programming interface that has a lot of nice Midi constructs already built in to do a lot of things. So I have a Midi send control message that will send a CC to a device port, a channel. Normally these CCs will be either on channel 1 or on channel 16, and then a CC number, whether you want to say send CC 48, and then a CC value, your 7-bit value 0 to 127 for that CC. Then I have a Midi send aftertouch poly message that will send a polyphonic aftertouch message on a device port on a channel with the two data items that I'll require for whatever the poly AT message required at the moment is. Then after that, the next most important thing is you're going to have to write 14-bit macros. These are built up from two 7-bit CCs, and you'll have to have some kind of a function that normally you'll probably have to create yourself, since this is not the normal 14-bit Midi message. This is a custom 14-bit message. So you'll build that up by sending in a control CC and a 14-bit value, or in the Lua interface it could actually be a 16-bit value, but you're only going to use 14 bits of that. And then in that function, you'll have to shift over the high 7 bits to get the MSB, the most significant byte, and then you'll mask out the high 7 bits to get the least significant byte, and you'll send those with two CC messages to build up your 14-bit macro. Now, the 14-bit macros, 45 of them use CC86 and another 45 use CC97. So you'll have to have some interface in there to differentiate between which set of 14-bit macros you're using. You can do this in a number of ways. You can have an argument that you send 86 or 97 or true or false or whatever you want to indicate that you're a CC86 versus a CC97 macro. Or you can just create two separate functions. One sends CC86 macros, one sends CC97 macros. That's what I do, but you're free to do whatever you want here. Then, after that, the most important thing that you'll need to support are what's called pokes. Pokes are sets of CC followed by poly aftertouch messages, and these perform various functions in the matrix. There's a matrix poke. This changes things that doesn't rely on formulas in the matrix. For example, you can change an oscillator type from DSF oscillator to integrated DSF, or you can change a wave bank waveform from saw to triangle to square, etc. Then there are other pokes called formula pokes, and these rely on the formula you're on for some reason. Normally these are related to something that uses W, like a shape generator, where you'll define the shape generator function in the W function. So that will require a formula poke, and for that you'll send the formula ID in. Each formula has a number associated with it, from 1 to 44, because there's 44 different formulas. So you'll send the ID of the formula, and then you'll send in the poke command and the poke data. In the matrix poke case, you'll send in the first poke command, which is a CC message that has a value of 56 and then a value of 20. On the formula poke, the CC is a 56 and a value of 19. And then there's the convolution poke. If you want to change, for example, the impulse response on a convolution or other convolution parameters, that is a separate poke that has a CC of 56 with an ID of 26. And then there are other pokes that do other things, like Big Bang pokes. The pokes we just discussed are examples of very small streams that only use 2 or 3 messages of information. But there are other streams, like the stream that you need to write all 48 values of a graph, where you will send a sequence of polyaftertouch messages to populate whatever the stream requires that you're working on. In our case, we need to write a stream that is a graph stream that uses the ID 56 with a value of 3. So to do that, I'll have to have some kind of a function that sends a sequence of polyaftertouch messages to fully populate all 48 values of my graph. You can do this various ways, but that's something that will have to be added on a custom basis. If you're not using graphs, then you don't need this function. But for almost all overlays, you'll need some combination of 14-bit, 7-bit, and polyaftertouch messages and pokes that we just talked about. Now, if you want to understand the full EaganMatrix Midi interface that's available, it's in the editor folder, HE User Guides, and you can go in there, and there's a file called hakenmidi.h, and this is the header file that's used for the EaganMatrix itself that defines the full EaganMatrix interface. There's nothing secret about this interface anymore. This defines the entire interface. So if you wanted to and you understood this interface well enough, you could, in theory, create your own editor in whatever language you want, for whatever device you want. There are a lot of people out there always asking for iPad versions of the EaganMatrix. Well, there's none in process of being designed that I know about, but if you know enough, you could create your own iPad version of the EaganMatrix, or maybe a mini version to do just what you need to do. Of course, with overlays now, the intent is that users won't have to go and program the EaganMatrix so much anymore. They'll use all these new overlays to create their sound. Let's take a little bit of a look at the Electra One interface for creating overlays. Obviously, you can use some other development environment, but the kind of things I'm doing here are the same kind of things you'll have to do no matter what tools you use. So let's go in. This gives you this nice GUI builder, and let's go through a few of the control options that you would normally program in an overlay. The first one is just supporting normal CCs. You'll still use a number of normal 7-bit CCs in your overlays. For example, if you want to allow the user to change reverb settings or convolution mix, gains, or a number of standard CCs that are still used that you'll program up in your overlays. Let's take the reverb mix, for example. This normally would be changed with CC24. This tool lets me set a min and a max range, 0 to 127, and a default that will come up when the tool starts up. I don't want reverb to be too high for the user, so I set that to a low value. I could set that to any default. And this just lets you set your parameter, here your CC, here 24, and when this comes up, you'll be able to change the reverb. And all other normal 7-bit CCs will work the same way. Now this tool lets me add routines to format the output of the values that the control will display. Instead of saying 0 to 127, you can format it to scale to anything you like. Here I wrote a routine to scale 0 to 100, which makes more sense, say, for percentage of mix output. You'll have to think about those kind of things too, how you're going to scale values to the user with output that makes sense. You don't want everything just to be outputting 0 to 127. And in the EaganMatrix, you can scale your values outside of its normal range, 0 to 1 or -1 to +1. But let's take a look at the more normal macro that you'll program, and that's the 14-bit macros. Now your development environment probably uses 16-bit words, or maybe even larger words, so as we discussed in the beginning, you'll have to mask off the 14 bits normally in your variables for this to make sense. But in this case, I can set a range now that maps to 14 bits and not 7 bits. So this tool lets me set for this 14-bit macro, which is one of the bipolar macros, a range of 8192 to 16383, and I'll default this one to the max, 16383. Its parameter is 40 because the macro that's associated with volume is CC40, and then this will have to call a routine that I created that we talked about to begin with that will set one of these 14-bit macros. In this case, it sets one of the CC86 set of macros. So you're going to have to think in terms of 14-bit values for a lot of what you do with these overlays. Now this happens to be one of the bipolar macros, which has a range of -1 to +1, scaled however your EaganMatrix would scale it on W normally. That means that the values of 0 to 8191 will all be negative, and the value of 0 to max starts at 8192. Now there are a few unipolar macros, the original 1 to 6 macros. If you program them and define them, they will be unipolar. Those will have a value of 0 to +1 using 0 to 16383. Now there's only 6 of them, so you have to reserve them in places where you need that extra resolution, because obviously if you have a bipolar macro and it starts at 8192 and it goes to 16383, and you have a unipolar macro that goes 0 to 16383, the bipolar macros have half the resolution of the unipolar ones, but still much more resolution than you'd have with a standard 7-bit CC. Now, it just turns out that when you write your EaganMatrix programs, at least when I write them, most of the controls that you need have a 0 to max range. So you'll find yourself using a lot of these bipolar macros using this 8192 to 16383 range. And of course, you'll scale it internally if you need values between that to map to whatever value you need in your program. Now, if we want to do something more complex, let's say I want to split the range so that my sequencing voices range from C0 to B4, and I want my solo line to start at C5 up to C9 so I can play the sequence in the left hand and play a melody above it. Well, to do something like that, I need to start using pokes. Well, let's go into some of this code. So here's some code that I have to do this split. Now, I'm not going to go into the technical details of this. If you want more information, you can look at the EaganMatrix Overlay Developer's Guide that goes into a lot more detail here. But you'll see, to do this splitting, I have to use formula pokes because I'm reprogramming W ranges. And W is part of a formula, so in this case, I'll use the formula poke. For other things, like changing the type of a wavebank, I have a control that does that, so your solo voice can change timbre, different waveforms. To do this, I needed to write a routine, and this tool very nicely lets you type in the name of your callbacks, the name of your functions that are going to perform your operations, and then you just go in to the code and add that function, and makes it very easy. When you activate your control, it will automatically call that function, and this kind of a GUI building tool makes developing these overlays very simple. So in this case, you'll see I use a matrix poke. This poke with the value of 99 and then the value, that sets the wavebank waveform to one of the wave types, sawtooth, square, or triangle. And that's how most of this program works, building up things and using 7-bit CCs, 14-bit macros, pokes of different kinds. For example, if I want to change convolutions, I can use a convolution poke, and I have a routine that does that. And this allows me to go in and change all my convolutions. I want to set some graphs, so I have a routine in this case, because I'm using all these offset graphs. This one actually sets the graph by calling successive send after touch poly after touch messages instead of putting things in a loop. I do it this way because I can actually go in and change individual values of the table here to create different fixed table values. I can also put this in a loop, and I have other ways to set the graphs in here that will basically just create an array, a table of my 48 values, and I'll have a function that will call and set it up that way. So I don't want to go into too much detail, but this is kind of the way that you go through and you'll program your overlays. Some things will be direct controls, some things will be functions that have to do something that you'll need to write a function for to do more complex algorithms. But the programming really is not that complex. You just have to know how you're relating your controls to the appropriate interface in your EaganMatrix preset. If you want more information, in the HE user guide directory folder of the Haken Editor, the EaganMatrix Overlay Developer's Guide will be there. I suggest you go through that. I have a number of other introductory videos on overlays that go into a lot of these topics, and I challenge the programming community here to try and create some of these overlays for us and see what kind of interesting, unique, and creative things you can come up with.